score. I haven't taken a look at the average, although from the few people I've talked to, it sounds like it went okay. If you did have any problems with it, actually taking it, please let me know sooner than later. Obviously, if a bunch of time passes and you were unable to take it for some reason, I need to know that like today or tomorrow. But otherwise, if content caught you off guard, that's a really good time to get feedback from the TA and the CA on how to improve, what went wrong. And of course, shoot me an email if you want to schedule some office hours, go over midterm stuff. I will be putting out the answers hopefully tomorrow. So most of the answers were quiz results in the past, but also some of them were not. So expect some solutions here in the next day or so. Just note that you'll have to kind of, well, actually, no, if I check a box, you should just be able to open up yours and look at the answers. So it won't be something where you have to like kind of cross-reference or anything. Okay, Kate, I think that hit your question. So hopefully tomorrow, I'll be opening that up. If I remember, maybe even tonight. I'll send out an announcement when I do open that up too, along with just some kind of basic kind of just remarks, I guess, averages, stuff like that. Quiz results for this quiz and not visible. Yes, correct, Arthur. So yeah, we'll get that taken care of pretty quick. They were hidden on purpose. I didn't want questions kind of cross-referenced between students. So that was that. Homework 4 got put out this morning. Hopefully it all works. I did a little bit of testing on it this morning. It should work. I believe the test cases are all good to go. It is a little longer, so get an early start. I think it's 60 points. So I guess last one was 50 something points. This one is a little longer though, because you are writing kind of operations for the dictionary type, which is going to operate as your kind of evaluation context, that sigma term. So you're writing that as well as the interpreter for lettuce, which involves defining the values for it. It also involves defining the expressions. So there's a little bit to this homework. A lot of it is just kind of translating between kind of a written grammar and the data type in Scala. So that stuff's pretty easy, pretty much free points. But the interpreter will take some work. So get started on that as soon as possible. You will need to do the earlier questions, do the later ones. So get started early. It'll be due in 1 week. So yeah, today, but next week at midnight. Normal deal. What else? There are some other logistics things that are now evading me. Any other questions from anybody about anything? I'm trying to think of what my remarks would have been. We had no recitation yesterday, so expect that to pick back up on Monday. And otherwise, I think we're good to bounce into stuff. I'm forgetting something pretty big. Probably be another midterm in a week or two. I got to look at the material, see when that should be. Oh, and I guess something else. We're nearing actually the end of the stuff we have to cover for the class. So if there are any special topics or stuff we covered in kind of up to now that you want to dive into a little bit more, especially on the functional programming front, or maybe adding language features, how do we implement this? Basically anything you guys want to do for the last probably 2 weeks of class, we can just do special topics. That's totally cool with me. It's actually a lot more fun to take direction from you guys and me just pick stuff. So there are a couple lectures I do have picked out. We'll cover the lambda calculus for one, for sure. I do like doing that. As well as maybe something on dependent type systems, which are kind of the really gnarly type systems that can do some crazy stuff and proofs and stuff like that. So we'll probably do that. How many assignments will you have in total? I'm unsure, and the reason I say that is because there were, I believe, 10 assignments in past versions of this class, but that was when we were doing a twice a week cadence. And we were really just doing once a week this summer. So we were just combining those in a larger homework. So I think it'll be around, this is homework 4, we'll probably have 7 or 8, I think, by the end of it. Towards the end, they'll get a little shorter. too. So yeah, not too much more as far as homework goes. I mean, plenty of points left. It's not like, we're done. We're definitely not done. This is week 5, 6, week 6. I think week 5 was last week. So yeah, so be on the lookout for that stuff. Yeah, and we'll definitely have more point opportunities. And towards the end, we'll probably have some option. If you want to make up points, there might be a project option for those that want to do one. I won't make everybody do them because it's a lot of work for staff to take that on. But for a few people, if you want extra points, you can probably make that happen. But those will be pretty large if we do them. So expect some work there. Yeah, that's all I can think of. Yeah, if you do have ideas for topics you guys want to cover, go ahead and throw those on Piazza in a thread, or email me. Either one's fine. And I can start prepping lectures for those. Other than that, let's jump into the material. So last week, we kind of finished off with some talking about our type system. I'm basically going to rehash a lot of it today, just kind of really hammer in those ideas, and we'll get into some of the more details as the lecture goes on today. So type system. For lettuce. So as you guys might recall, I guess our intro question, what are type systems? Anyone have thoughts on that, or an intuition? What's type system? What do we use them for? What are they good for? What aren't they good for? What do we think about type systems? Do we like them? Conlon likes type systems. Why do you like type systems, Colin?
Well, I mean, I'm not exactly sure what a type system is, but I'm thinking, well, I guess, I don't know. I think it like adds a point that I feel like we've been like driving in on, like, hey, what if it's not this type? And some of the semantics. So I think it helps solve some of that.
Yeah, it solves some problems. What problems might manifest where types? What kind of problems do types solve?
Add everything in a list if it was a string.
Yeah. So like when an operation is supposed to operate on a certain type of thing, and that's not the thing you're giving it, right? So these type errors, right? So type systems remove type errors from runtime. And they kind of move them before compile time, right? So we can like always do type checking on a program, at least in the languages we're writing. You can always give types to stuff. That's kind of the beauty of this lettuce language. It's not always the case that you can do full type checking. In a language, it usually is, but not always. There's some languages with systems where the types actually can change at runtime, and they can do really gnarly stuff. It's like JavaScript has some really weird, you can do some weird kind of meta programming with the types, and it can sometimes make type checking beforehand not safe. And usually you don't do type checking on stuff like Python and JavaScript. It does it at runtime. But if you can still run type checkers on them, and sometimes they'll fail. Even if you did a type check, they'll sometimes still fail at runtime if you're doing certain weird tricks. There's some notes in chat. Yeah, so they're good. Oh, I really like that, Brian. So they're good for static code analysis. That's kind of what I said before compile time. It's a type of static analysis. Now, it's not usually what we mean by static analysis, but the static analysis usually pertains to kind of other ideas around performance, resource usage. But type systems definitely fall into that camp. Usually they kind of get their own category, but they're definitely a type of static analysis. That's opposed to something like a dynamic analysis, where dynamic analysis will often run at runtime and tell you things about the program as it runs. You guys will use tools like that if you become commercial developers. Usually there's some esoteric tool that you will actually become really good at using to do some kind of analysis on your programs. Linters, for instance, if you guys have used those, they kind of clean your code up. That's another kind of type of static analysis plus program transformation, kind of cleans up your code. Yeah, so good. Is type checking type systems, are they in the semantic or the syntactic domain of programming languages? Semantic. Why do you say that? Yeah, it doesn't have anything to do with the symbols at all, right? So another way of thinking about this, same way, is like it's ascribing some meaning to the program, right? It's not quite the operational meaning. It's not what it's computing, but instead it's what type of stuff does it compute. So it's, instead of saying the result is 5, it's kind of saying, well, the result's going to be a number. We don't want to run the program, so we don't know what number it is, but we know it's going to be a number, right? So it does that. So yeah, a type of semantics concerned with the type of the results of a program. Let's see if I have anything else in my notes here. Yeah, so it's trying to answer what type of result will we get when we run this. Now, follow-up question onto that idea. So let's think more about kind of lettuce, or kind of our concrete example here. Does every expression have a type? I'll let you guys think on that for a second. Yeah, so a couple people are saying duh and yes in chat. We think so, yeah? So it's kind of a loaded question, and as I was asking it, I realized it's kind of a loaded question. Strictly speaking, no, not every expression will, but they will all have type checking rules associated with them. So as long as the program is well typed, every program will have a type. So if it's well typed, we'll be able to give it a type. So like, say let bindings, those have a type, right? And it's not the type of what's bound, it's the type of the resulting expression, right? Functions always have a type. Those are those arrow types, right? What's another example? Well, like obviously the number operations all have a type, right? Yeah. So Graham, good. So Graham asked, so you're saying no, but only because we could write nonsense. And that's basically the idea, is I could try and add, say, a string and a number together, and that would be nonsense, right? A type error. So in the absence of type errors, yes. And I think that's the kind of the result here that I'm looking for. Is that how you spell absence? Okay, we'll go with yes. So this is a pretty powerful tool, right? If I can always say, you know, I have this program, I don't want to check every execution of it, right? For maybe a type error, right? And that could be hard to do. You know, remove this whole class of errors from my program. You know, it says my program is 100% for sure safe with respect to type errors. And that's a powerful thing, especially when you start to think that if I encode my types just so, and I create new types, maybe I can make any kind of program as safe as I want it to be with respect to certain semantics, right? And eventually types actually start becoming these semantic, like giving meanings to programs themselves, which is kind of a more meta idea. It's like to say a program's a number, that's like semantic stuff on its own. Kind of not even removing it and setting it at the meta level. It's like within the system, it's assigning meaning to the program, right? So it's kind of semantics in more than one way in a certain sense. Yeah, so let's see. Let's go ahead and define the type of types. Let's do that for just our lettuce language. So we'll have a few types. And let's see if you guys can help me define this. So defining types, or defining type. Okay, and type, we'll have kind of that normal form we're looking for, so it's grammar. We'll call it type, 2 colons and an equal sign per usual. What kind of types do we have in lettuce right now? Should be 3 of them. A couple obvious ones, one might not be so obvious.
No.
Yeah, so a num is one, so we'll have a num type. An obscure French mathematician just put a whole bunch of answers in chat. Now, I think is that John? No, who's Bourbaki today? I don't know. I can't tell who that actually is. Yeah, so fun little, one of the students popped in today with the name Bourbaki, which is, or Bourbaki. No, my French pronunciation is really bad. Bourbaki is a interesting French mathematical author. And I say author because it's not really a person. Bourbaki is this actual, it's started as a secret society that published math papers in France. So there's like 20 or I think it's 22 authors originally in the Bourbaki Society. And they published a whole bunch of papers and no one knew who this was for years and years and years. And only later did we find out, okay, this actually wasn't one person. This was a large group of French authors. And only later did we know this, wasn't an individual. There's some really, did I get the phonetic? It's Bur. Oh, I did say that almost right. It is just Bourbaki. Is the phonetic. I think, yeah, so now I'm getting all nerdy about the IPA. If you guys don't know what the International Phonetic Alphabet is, it's really cool. Something to look into. But yeah, so Bourbaki, really interesting figure. I guess you could call it a figure in French mathematics. The French are really known for some awesome math. And have a lot of the really cool, interesting stories. A guy named Grothendieck, who is a more contemporary mathematician, contemporary meaning like 70s and on. Really interesting guy you guys could look into. Another one is Évariste Galois, who is who's younger than most of you, I believe. He was a founder of group theory and abstract algebra, died in a duel, I believe at 21 or 22. And there's a lot of thoughts about what would have happened to the math world if he would have lived like even another year, let alone his whole life out. That was during the French Revolution. So if you guys are math nerds like me, obviously I've been rambling about this for a minute. French mathematicians are really cool. They got some really cool stories behind them. So like Grothendieck was basically became a secular monk doing mathematics, just a crazy dude. And then tried to take all his math back and say, I want everything unpublished because I don't like capitalism. And that was, yeah, it's just crazy. So anyway, sorry for that dive for those that weren't into that. Cool. A lot of thoughts on Galois in chat as well that I will leave in chat. Yeah, so we got Nat, Mr. Bourbaki, or whatever the proper honorific would be for Bourbaki. Said Boole is another type. So we got Boole types. And let's see. So Expert, Val, and maybe we could implement those, but in lettuce right now, those aren't types yet, right? So we don't have, for instance, like just and nothing. Those aren't, we haven't implemented those in lettuce. We've implemented those in Scala at the Scala level. If we wanted to add those to lettuce, it would be pretty easy to kind of start building up a standard library within lettuce, which we could do as well. Same, and Val, same way. Those are all types that are at the Scala level, right? That we're using, but not necessarily in lettuce yet. So any thoughts on our last type? This one's a little bit more, I guess there's more meat to it.
Type error.
No type errors here. I'll address that in a second. Now we will still have type errors implemented in Val. That will still be there. Because you can still obviously run a program that hasn't been type checked. You could do that. So we'll leave those there, but error won't be a type. And more importantly, type error won't be a type. Actually, both of those could be valid types kind of almost on their own. What's another type that we have in Scala or in lettuce? We talked about them last week quite a bit. Actually, pretty much all week. That's what we talked about. We have numbers, we have bools. It's not a data type per se, right? So we differentiate data types from this other kind of type. There's types that have data and represent stuff, right? So that's like your numbers, your booleans. In Scala, say, your maybe type, your lists, strings. But then there's another type that we've encountered, function types, right? So function types we typically won't call data types because they don't hold data. They actually do computation, and that's a different kind of type per se. So yeah, so we'll also have a fun type. So we like having fun. Or if you're feeling funky, we could have a funk type. I've gotten a lot of mileage out of that joke over the years. Either one of the names works. And kudos to Brian for saying closure. That was almost there. And rows as well. We could also implement strings. That actually might be in one of the homeworks coming up as well. So we can implement as many data types as we want. Right now, we just have these three. So fun type or funk type, I don't really care which name you use as long as you're consistent per usual. Funk type, is it a type on its own or do I need to add more stuff there? You guys should kind of know this from programming in Scala a little bit too, and in class with me. When we have a function type and we give the annotation, do we usually just say, oh, it's a function? Or yeah, so it can be parameterized in some sense, right? Thanks, Brian, for that. So function types will often have other types, right? It's a function from number to bool, or from number to bool, right? So it's never just a function, right? So we'd actually say it's a function, and then it'll also have two more types, right? We also sometimes call this the arrow type because we often write an arrow in between, right? So something like A arrow B is typically what we would see in concrete syntax. That's how we'll write it too in lettuce. That's the concrete syntax, is A arrow B, right? Where A and B are num or bool, or maybe another function type, right? So we still have functions on multiple parameters here. That's still around. Oh, okay. So sorry, Brian, for giving you credit where credit was not due. Yeah, so we won't have type parameters necessarily yet, because that would require us to implement polymorphism. So parameters meaning like a type variable in the type, right? Where we say we have a list of A to A, right? Like that head function that just takes off that first element. We can't do that yet without implementing polymorphism. And if we want to do that, we definitely can. That can be one of those advanced topics we talk about, which I don't think in my time here we've ever gotten to, but polymorphism is a really neat idea with type systems. So you could actually do polymorphism here if we had a polymorphic type like lists. You could actually program it in Lettuce, and Lettuce would run that program fine, but it would have a hard time type checking it, which is the interesting part. So how do you keep track of those types? That would be a fun dive if you guys do want to do that. So throw that in Piazza if that interests you. Cool. So those are the three types we'll have for now. I'll often write kind of num, bool, and arrow. And that's the concrete syntax, which we probably already knew, but I'll just make a note of that here because I guess we never made it super explicit. Now that we've done that, let's address why there aren't errors. Can anyone take some thoughts? Why might not there be errors as a type? And I'll give you this example. You know, if we had errors as a type, right? So if we had another type there said error type, I could write a program like this: let x of type error equal something in something like that. Does that make sense? Why not? Well, no, let's assume we do have one, right? So that's part of the assumption. Let's say we do have errors. Yeah, what operations do you do with an error? In Lettuce, there are none, right? What? Not return. There are stuff you can do with errors though. And I'll ask about that in a second. But if you had an error in your program and you knew it was an error, why is it there? That's the better response, right? It's like, why would you just leave an error there? So there's a little bit of kind of nonsense here too, because that's a type annotation. I'm saying that's an error. But having errors be able to be programmed into your language, you don't really want. We don't want it to exist inside kind of what we write. So we're going to keep it separate. And so instead, when we error handle, when we do type checking and type inference, we'll handle errors with the maybe type. Okay, where we'll have either just value or we'll have nothing, and nothing will represent a type error when we type check. Cool. Or it'll be a just type and then nothing. So we'll use maybe to deal with that problem. There's kind of another more kind of epistemic, for those of you that know what that word means, reason why. And epistemic is kind of the study of knowledge, right? Kind of at a higher level, you know, think Socrates, Plato, Aristotle. Why might we not want error as a type? Kind of built in. If types are representing our knowledge about a program, error represents us not having knowledge of a program. It's kind of the antithesis of what types really are, saying I actually can't give this a type. So it's not a type, right? If we stick to our definition of what a type is, it's just not a type. Types are what the program produces as a computational result. Error is not really a computational result. It's the lack thereof, right? So we kind of pull it out to keep our arena a little bit more kind of clean, pristine, and it does separate out something that shouldn't otherwise be there, right? Yeah, and you can't perform, Pseudo says you can't perform operations on errors. Now, if I were programming in Java, for those of you that have done that, which might be a minority, what can you do with an error? I'm sure you can do this in Python and a bunch of other languages too. Yeah, there we go. So you can do error handling. You can catch errors. You can do a try catch block. Strictly speaking, that's an operation on errors, right? So in some sense, when you get into stuff like Java and these languages that do have error handling, you get into this weird space where the type system, I think they actually do, even in those type, they do give errors a type in those systems, and it makes sense in those systems because they have errors as an object that you can work with. Here in Lettuce, we don't. Errors are our fail state, and we keep them kind of separated off. In functional languages, that'll always be the case. You'll never encounter exceptions in, say, like a Haskell or something like that. You can in Scala, but that's because Scala is implemented on top of Java. It's supposed to kind of meet in the middle. So just something to know. You definitely can do stuff with errors, but in Lettuce you can't because it's a nice, clean little functional language. So, and we won't touch errors beyond that because error handling is a mess to introduce to languages, and it can get kind of hairy. So, again, possible area for a special topic. We do want to cover that though. Cool. So talked about that, why we don't have errors. That'll come up again too as we start to kind of write out some definitions. We're going to need to also update. I'll move to another page for this. We're going to need to update Expr a little bit. Okay, so Expr is mostly fine as it stands. So most of our definitions are going to stay as is, or most of our constructors rather. We're going to need to change 3 of them. So anywhere, and we touched on this a little bit last week, anywhere there's a variable that's new, a newly bound variable, anytime there's a binder, we have to give that a type. Otherwise, we'll hit a snag when we do type checking. We saw that last week in the rule we did do. But we do need to have type annotations anywhere we bind variables. Where can we bind a variable in Lettuce right now? There are 3 places. Let bindings, right? Let statements. So let statements are kind of the first most obvious one. So let is just going to change a little bit. So we have let string, and after the string, we're going to put type, and I'll kind of put the changes in red. If we don't have a type system, we don't need this extra stuff. So just know that. So we have let string type, Expr, and Expr. Okay, otherwise it stays the same. Yeah, so Brian says somewhere in function definition or function calls. Not in function calls because there's no binding happening, but yes for function definitions. In a function definition, where does binding occur? Anyone tell me, in a function definition, where do we bind something? Let's write it out. So if I have function x plus x, right? That's a whole function definition. Need nothing else. Where's the variable that could be bound there? Where? Because there's 3 of them.
It's the parameter.
The parameter, right? So the parameter is a binder, right? It's binding that x. It hasn't been given a value yet, but later on when I give it a value, I guess it, strictly speaking, will bind at the application. But here there's a binder, right? There's that x. So here when we get to the concrete syntax, and I'll leave this here for that purpose, we could have something like x of type num. we'll always give annotations now to our function definitions. So we have fundef. I'll still take a string. We'll give it a type this time. And an expr. Okay. Where's the last place we could see some kind of binding occur? Not in closures, because closures are just a runtime object, right? They're a value. So in type checking, we won't ever encounter a closure. We could think of types actually as being like values in that they're the result of a semantic computation. It's like when I do the other kind of operational semantics, I'll get a computational result, a value. When I do type checking semantics, I get a type as a result. So they're similar in that respect. So closures, push those off to the side for now. What's the other place I could have binding occur? Let rec. Yeah, why let rec?
Sort of that same thing. This one's got like 2 strings and 2 expressions. I think like one of the strings is like the function, the binding function.
How many types do we think we need? This is a good question. So there's definitely one for the function, right? Yeah, giving it a function type. Yeah, then the parameter better have one too. Yeah, so there's at least 2. There's 2, right? So let's find those out. So a good marker is that anytime we see a string, that identifier token, right? So strings here, we're going to give it a type, right? Because that's where the ambiguity arises, is from bound variables. Bound variables are always going to be given from a string. So naturally, we'll have those coupled together. So let's do that. So we also have let rec. And remember that let rec is really just a combination of fundef and let. So if we think about it, if we slap those 2 together, well, you know, the let part says this part of the expression becomes a fundef, right? So we can just kind of combine those together, which is essentially what happens. So we have a string and a type. That's for the name of the function and the function type. Then we have a string. I'm bumping this to another line because I'm going to run out of space. String and a type, that's for the parameter. And then we have 2 expressions. One is the body of the function, and then one is the rest of the program. Okay, that was a lot, so I'll also write this an example down here in the concrete syntax. So let f be of type num to num equal function x, say of num, and we do x plus 5, for instance, and then in, say, f of 10. So that's an example, right? And I'll actually kind of annotate this too. So we have a string, we have a type, we have a string, we have a type, here we have an expression, and here we have an expression. Is that good with everybody? Everyone on board so far? Is that annotation helpful a little? Hopefully make it a little bit more concrete. Let's see. Sweet, so that's our update to expressions. So as you can imagine, the rules for type checking, these 3 are gonna be a little bit more kind of complicated. When we start to write those, they'll have a little bit more going on, just because we have types kind of baked in the expression. They'll be simpler in a certain respect, but they'll also manipulate the environment, the context a little bit. Speaking of, let's talk about the typing context. So like with Sigma, when we have variables, we need to keep track that ledger of what we've defined, right? So that's our gamma in this case. So let's call this typing context. Gamma. That's not a very well drawn gamma. Should look more like that, something like that. It's usually, or sorry, actually remove word back. It'll keep track of types of variables during type checking. I should say during type checking and type inference. And I'll talk about the difference between those two here in a second. These contexts will usually be implemented as a dictionary. Or map. Maps are dictionaries, capital M maps, not the same as the function on lists. Well, yeah, that'd be on strings to types, right? So a string to type dictionary. What else? More notes on the context. I don't think I have much. Similar notation to gamma. Or in evaluation environments. Environments. Or sorry, to sigma. Or yeah, sigma, not gamma there. And yeah, it's denoted with gamma typically. Sometimes it very rarely does that notation ever change. It's almost always gamma. That's about all I have for typing context. So yeah, that's good to know. We'll use those in our inference rules. We'll look at the judgment, that relation here in a second. Yeah, so let's talk about the judgment form before I talk about checking versus inference. So form of typing judgments or rules. Cool. We did this last week, so this is more review, but I did want to kind of elaborate and go into this a little bit more. So the form is always going to be, in some context, gamma. We have some expression E of type tau, or some type T. The letter doesn't really matter here. And I'm going to annotate this a little bit. So we have a typing context, gamma. We have an expression, E, and a type, tau, or T. And in plain English, this says, in context, gamma, expression, E, has type tau. Okay, so if you ever see that, have a hard time reading it, just like the operational semantics we used, you can kind of convert it in this English sentence. That's what it means in English. Okay, it's just symbols for that. Writing out the sentence, the English sentence every time would get really old after a while. For a long time, mathematicians did that, and it got really old after a while. So try read a paper from 1600s. It's rough. It's all in English. There aren't any symbols. That came much later. So yeah, kind of a pain, but get used to reading that stuff. It'll definitely, actually, some life advice for programmers. If you guys can get good at reading symbols and stuff like this, mathematical notation, you'll do really well, because you'll be able to kind of go probe research, like stuff I do. Read research papers, maybe implement that at companies, right? And if you can get good at that, a lot of times it takes a little bit more training, maybe a master's degree. But if you can do that, money, man. I mean, it'll treat you well. And it's just how you keep learning in this field too. So I was never good at reading kind of symbolic language like this until I got here for grad school. And it took 2 years to get comfortable with it. But once it kind of clicks, once you get used to it, it really pays off. So something to kind of maybe work at. Just some career advice there. Yeah, and if anyone ever wants help with that stuff, yeah, you know who to find. Hit me up. Cool. Let's keep moving. Or first off, any questions about the form of the judgment rule? Of course, we can replace E and gamma and tau with specific, expressions, types, and gammas. So those might look a little different in the rules. Of course, that was how the same way with the other inference rules we were using. And we'll get to that here in a little bit. We'll do a couple of rules today, probably, before we call it. Yeah, and then one more note, and this is actually, I really like making this remark. So type checking versus type inference. And inference should only have one R. That looks better. Does anyone just reading those know the difference? I'm curious. Fake bonus points if you do, or I'll like you more, or something. Any ideas? Chat, I'll actually give you guys a second. In the room, people. Think on it, but I'll tell you guys when to answer. Oh, go ahead.
Is it like validating that an object is a type versus determining what type it is?
Right on. I like it. So type checking will be kind of validating a type. So the example is, if I were to kind of write this as a function per se, it would be saying, does this function have this type? If I say this function has this type, tell me if I'm right or not. So, or not function, but program, right? Is this program of type T? You also think of it as more verifying the type. Okay, so I already have some idea of what it is, right? I'm saying just, is it this, versus type inference. Which is actually figuring out the type. So say my program doesn't have types in it. Let's figure out where the types are. The reason we were putting those type annotations in partially was to make type inference easier. With those annotations, we're going to be able to do type inference, right? Determining the type of a program. And kind of the corresponding question would be, what type does this program have? Now, what's the difference between these two? If let's think about them maybe as functions. So let's say I get from type checking, I could get either a type or a Boolean out, right? A type, maybe it's the same one I passed in if it's right, or it just gives me kind of nothing if it's wrong, but we'll say a bool. I'll put TC here, type checking. What does it take as input if we were to write it as a function? Type checking. What does it need as arguments? Program's a good start, I would say, right? So it takes an expression and it says, is this well typed? But I need to give it a type too, right? So does expression have this type? And we'll also give it a gamma as well. Okay. These types won't be super useful right now, but it might be. Whereas type inference, I'll write TI for that. Still taking a gamma, more for bookkeeping reasons, and an expression. And what do we think this will output? Probably not a Boolean. What ought this spit out? A type, right on. So a type, but not just anything. So we'll also have it kind of wrapped up in a maybe. So it might be a type, because it could also still be not well typed. So that's where that maybe comes in. So when you guys start to define your type checkers later, which I think is going to be still 2 homeworks away, it's a little ways out. So I'm going to drag out type checking this week. Kind of get us synced back up again, hopefully. You'll use a maybe type to kind of represent type errors there. But otherwise, just outputs a type for kind of our purposes. So note that they're kind of different, right? They seem like similar things. They both check and see if the program is free of error. They both do that equally well. And actually, in some sense, these are both stronger than that, right? Because you could also just say, are there any type errors in this? And that's almost asking a slightly weaker question, right? It's not giving you a type. It's not checking a type. You never see that. You always give it a type to check. But yeah, because otherwise you'd be doing inference. So yeah, I guess these two kind of, they're the same and different in certain ways. They're 2 different ways of checking the type of something. And they're both useful for different instances. I will say type checking is a lot easier to do than type inference. For our language, they'll actually end up being the same thing. They'll be really easy to do. You'll actually just do type inference when we write a type checker. Later on, when you start to introduce polymorphism, starting to introduce more types, maybe gnarly function types, something different, it can get more difficult. And there's a lot of other stuff you have to keep track of. You know, if I give, say, a list of A to A, you know, what's that A going to be when I instantiate that? Does it type check? You know, actually deal with polymorphisms, this big, nasty mess. So, yeah, just something to think about. Again, we might touch on that in a few weeks, but something to know. There is a difference between those two. So when I talk about kind of either or, drill down in me if I'm using those kind of weakly and not really saying why there's a difference. So normally here we'll be talking about both for lettuce, because the process is very similar for both of these. Cool. Let me just take a look at my notes, make sure I didn't miss anything. Errors, check. Cool. Let's start taking a look at some inference rules for type checking. And we did a couple last week, but let's forget we covered those for now, and start from scratch. Let's start with something easy. Do we think we can write an inference rule for, say, type checking a number, just a value, or just a kind of constant number, just a number?
Could you scroll it down just a little bit so I can get that type checking?
Up, right here.
No,
Is it-
just those last 2 lines.
oh, okay, cool.
Thank you.
What was I writing? Inference rules. For type checking. We'll start with numbers. Remember, the expression here is num, and then there's some number n inside, right? Let's write, oh. Did we get all caught up with those 2 lines?
Yep, good to go. Thank you.
Perfect, cool. Okay, so let's start with a big ol' line for an inference rule. And what can I write on bottom? Well, I'm going to start by writing our gamma entails, you know, the kind of boilerplate notation. A colon for the has type of stuff. Now, what goes on either side of the colon here? What goes on the left side? That's the easier one for sure. Just n? Num n, right on. So num n. And what goes on the right-hand side? Num type, right? I'm gonna write in the concrete syntax for these rules. So I'm just gonna write num, lowercase num, because that's what the concrete syntax will be. It's a little inconsistent. But later on, when we start dealing with functions, it gets kind of nasty if I don't write this way. So yeah, left-hand side I'll leave as our abstract syntax. So is that all we need? Do we need any premises on top? Why not? Yeah, there's no evaluation. N's a number already, we know, because the constructor will only actually take a number. So Scala is doing a little bit of work here for us in making sure that that n is for sure a number. It's baked into the expression, right? So nothing on top. That's the whole rule. So that's type checking for numbers. Do I need an error rule here? Could this go wrong anywhere? N's got to be a number. Yeah, it's restricted by the syntax, right? So we don't have to worry about it there. Syntax restricts it. Kyle, any thoughts? Just staring deeply into my eyes. Okay. Like you're staring me daggers there for a second. I'm like, did I do something? Am I in trouble? Okay. Cool. How about Booleans? Just regular old kind of Boolean values, or yeah, values are kind of overloaded term, but bools. Which has the form bool, say B, put B in there. What goes here? Somebody give me like the whole inference rule, you think? Just in one go. Any thoughts?
Like gamma entails.
Okay, so gamma entails.
Yeah, then bool B as type bool.
Bool B as type bool. Anyone see anything wrong with that? I don't. I like it. Cool. Yeah, that's a rule for bools. We got the 2 easy ones out of the way. All of the rest are actually quite a bit more involved. Sweet. So let's move on. Let's do like in the arithmetic operators. We'll just write one rule for all of them because we know there's that kind of shorthand form we could write. How could we write those? So ops plus, so this would be stuff like plus expr would be the form, I guess, from kind of being inconsistent. Or it'd really be plus E1, E2, I guess. There'd be like minus E1, E2, etc. Okay, I'm going to draw this line for the rule. Let's see if we can get this one out there. What can we start with? It's actually a really easy start, kind of like the last two. Yeah, so we start with that gamma and tails pretty much always. Sometimes gamma will be a little bit more specific maybe, but not yet. So gamma and tails what? What? Yeah, so we can just, we'll put op there. And we'll specify what op is in a second. Don't leave me hanging, Aaron. What's the rest?
Then on the top,
No, we're still on the bottom. You didn't finish that. Op E1, E2 is what? We're missing part of our judgment form. What are we missing? You just have the gamma and tails part. Does it say anything about a type there? I don't see any types there, man. We need a colon and a type, right? What type should that have? These are all for binary operations. They all have the same output. Num, right? So the num type. Now we can start talking about the top. The first thing we're going to do is define op. And we'll say op is something in the set plus minus mult, etc. So those binary operations, the output has to be a number for these, right? For obvious reasons. So that's the first part, or the easy part. What else needs to be true for this to be true? So we're saying here that these operations produce something of type number when. Okay, how do I write that on top? Not as an element of. Now you're trying to go back to set theory, which is fine. It's not entirely wrong, but well, it is entirely wrong, but you're kind of thinking the right way. Just because we're being good with syntax, right? So we'll use the same gamma notation, like gamma and tails notation, right? So here we'll have gamma and tails, you know, I'll start with E2 because I'm writing the wrong way. So gamma, that's an F, not a gamma. Gamma and tails, E1, E2 are of type number, right? So it's funny, you said the right answer in English, but you just didn't make the conversion over to the symbols, which is fine. There's nothing wrong with that. The is element of lives in set theory land, and we're in our own stuff here. We're not using set theory right now, except for op. Op is where the only place we cheat, which is good. With Sukanya on Monday, you guys will talk a little bit about why we use inference rules. And talk about proof trees and stuff. When we use set theory, we haven't really defined inference rules for set theory yet. We have for these judgments, right? That's why we don't want to use subset, is because right now we're defining rules for how to prove that. And so if I go like have a number, I can go and find an inference rule to prove whatever I need, because I've defined it. If I'd start bringing set theory in, it gets a little bit more hand wavy. We don't want to do that here. So not bad thinking though. I mean, that's definitely, sometimes that's how you would kind of do that, but not here. I like it. That's our complete rule for arithmetic operations. Cool. Could we have an error here? Could I? Yeah, how would I write that as a rule? Can I? Can I write, like if I have a type error, is there a way to represent that in this form? Why not, Maddie? You're about to shake your head. Right. We left type errors out on purpose, right? And so if I wanted to put a type error, where would it go? It'd probably have to go there, but I'm not allowed to put it there. It's not a part of type. I did that very much on purpose. So with type checking, it's not like our other rules where we had to have an output type, have error be an output. Here, we actually just construct rules for the good cases. Because anytime there's not a good case, we won't be able to derive these rules. So we're only defining rules for the good cases. We'll be able to like write a proof for that using the inference rules. You know, using say this or that. And if we can't derive a proof tree for these inference rules, and we'll show you proof trees on Monday. That's the whole thing with Sakhani on Monday. You don't have a well-typed program. And then you put out error. That's it. So the error is anytime I can't apply a rule to get a typing judgment. That's it. That's all the error checking you need. It's like, I just can't find a rule. You're done. You know, you don't need to define extra rules for that. So where there's ambiguity here, we actually get some free kind of work, which is kind of nice. I think so. Now, when you go and program this, it will be that easy, but you have to then output nothing. You do need to have an output. And so you'll use the maybe type to handle that. Cool. From Burbach Key, later generations will regard set theory as a disease from which one has recovered, is a quote from Henry Poincaré. Very smart guy too. Also another great French mathematician, and he's right. Set theory is bad, but that's a whole nother discussion. I'm a type theorist, so I would say that. Yeah, so no type errors. Let's see. We only have 4 minutes left. Get out of here. We'll wrap it there for the day. Yeah, tomorrow we'll pick up with the more complicated rules. You know, so far we've just had this one with that even had a premise. Tomorrow we'll start dealing with, okay, well, what do we do with variables? What do we do with, you know, let bindings? These things that have variables in them. Right now we've stayed away from those. We'll talk about those tomorrow and start dealing. Gamma hasn't really gotten used yet. We'll start using gamma tomorrow. So thanks, guys. Have a good one.
Professor.
Thank you.